Hello everyone. In the last few lectures, we built a new structure called a sigma-algebra. At first, it looks like just a collection of sets, but later we discover something deeper. A sigma-algebra is really a structure of information. It tells us what can be observed. But today, we will discover that information is not enough, because information does not tell us what it means for 2 points of A to B close. Last time, we studied the co-countable sigma-algebra. A set is measurable if it is countable, or its complement is countable. So this structure treats countably many points as small. In some sense, countably many exceptions can be ignored. That is already very close to the measure theoretic idea of ignore negligible sets. What did this example teach us? It taught us that a sigma-algebra is not just a random collection of sets. It controls what information we are allowed to observe. Small sigma-algebra means little information. Large sigma-algebra means more information. But here is an important point. Information is not geometry. Now consider the sequence. 1, 1/2, 1/3, 1/4, and so on. Everyone says 1 over n converge to 0, but what does that arrow really mean? What does it mean for a sequence to approach a point? This is no longer a question about measurability. This is a question about closeness. A sigma-algebra can say that set is measurable. It can say this even is observable, but it cannot say this point is close to that point, and it cannot explain why 1 over n approach 0. So we have reached the boundary of sigma-algebras. To talk about limits, we need to know when points are near each other. This is the missing idea. A sigma-algebra gives information, but convergence needs geometry. So if we want to understand limits, we need a new structure. The first attempt is distance. On the real line, we measure distance by absolute value. The distance between x and y is absolute value of x minus y. This gives us metric space. A metric space is a world where closeness when it can be measured non-measurably. But for convergence, distance often contains more information than we need. Maybe I don't care whether the distance is 0.001 or 0.000001. I only care whether the point is inside a sufficiently small region. So maybe exact distance is not the real hero. Instead of measuring distance directly, we look at region around points, interval, balls, neighborhood. These are open sets. Open sets encode the idea of being nearby, without always keeping the exact non-mergeable distance. Now, topology appears. Topology is a collection of open sets. At first, this sounds very simple, but structurally, it is powerful. A sigma-algebra describes observable information. A topology describes closeness. There are different structures solving different problems. This is a bridge. Sequence leads to convergence. Convergence needs open sets. Open sets from topology. Topology generates Borel sigma-algebras. And Borel sigma-algebra allow measure theory to interact with geometry. So topology is not a random new topic. It is a bridge from limits to measurable sets. Now we know why topology should exist, but we still have one question. Can any collection of subsets be called open sets? Of course not. So next time we will ask, what roles must open sets satisfy? And that will lead us to the definition of a topologic.